When installing a screen room for pulse power experimentation, isolating the ground is crucial to prevent ground loops and electromagnetic interference (IME) that can disrupt the experiments. Firstly, install an isolation transformer between the main power supply and the screen room. This transformer has primary and secondary windings that are electrically isolated. Secondly, connect the primary side of the transformer to the main power supply. Thirdly, connect the secondary side of the transformer to the electrical load inside the screen room. And fourthly, connect the neutral terminal of the secondary side of the transformer to a dedicated isolated ground rod. It's important to maintain safety while isolating the ground. The screen room should still be bonded to the building grounding system for electrical safety. This ensures that fault currents have a safe path to ground, protecting equipment and personnel. The transformer's isolated ground rod should be separate from the building grounding system. This separation prevents fault currents from flowing through the building's grounding system and interfering with other equipment. All electrical work, including the isolation transformer and grounding, should be inspected and approved by a qualified electrical inspector to ensure compliance with safety codes. Isolating the transformer's ground does not make all grounds and bonds equal potential. Only the isolated ground rod and the secondary side of the transformer are isolated. The screen room's frame and all equipment inside the screen room are still grounded to the building's grounding system for safety. The benefits of isolation includes preventing ground loops to minimize EMI, protecting equipment from electromagnetic interference, and improving the accuracy and repeatability of pulse power experiments. When dealing with electrical installations, always adhere to the National Electrical Code, or NEC. Several articles and tables within the NEC are relevant to grounding and bonding. Article 250 covers grounding and bonding, providing comprehensive requirements for electrical systems. Section 250.20 discusses the general requirements for grounding and bonding of electrical systems. Section 250.24 covers grounding requirements for separately derived systems, such as those using isolation transformers. Section 250.50 addresses the grounding electrode system, which includes ground rods and other grounding electrodes. Section 250.96 details the bonding requirements for metal enclosures and equipment. Table 250.122 provides the minimum size of equipment grounding conductors for grounding raceway and equipment. Additionally, ensure compliance with local electrical codes, which may have additional or more stringent requirements than the NEC. Coordination with the local electrical inspector is essential to ensure that all work meets the applicable codes and standards. When installing an isolation transformer, several factors need to be considered. Firstly, determine the appropriate size and capacity of the transformer based on the load requirements of the screen room. This involves calculating the total volt amps, or VAR, of all equipment that will be powered by the transformer. Secondly, select a transformer with the correct voltage rating for both the primary and secondary sides. Ensure that the primary voltage matches the available power supply voltage and that the secondary voltage matches the voltage requirements of the equipment in the screen room. Thirdly, choose a transformer with a suitable insulation rating to prevent electrical breakdown between the primary and secondary windings. The insulation rating should be high enough to withstand the maximum voltage difference between the windings. And fourthly, consider the transformer's efficiency and energy losses. A more efficient transformer will reduce energy consumption and operating costs. When connecting the primary side of the isolation transformer, use appropriately sized conductors and overcurrent protection devices such as circuit breakers or fuses. The conductor size should be based on the transformer's primary current rating, and the overcurrent protection device should be sized to protect the transformer from overload and short circuits. Ensure that all connections are made in accordance with the NEC and local electrical codes. When connecting the secondary side of the isolation transformer, use a separate grounding electrode system for the isolated ground. This typically involves driving one or more ground rods into the earth and connecting them to the neutral terminal of the transformer's secondary winding. The ground rod should be located away from the building's grounding electrode system to prevent ground loops. The size and number of ground rods should be determined in accordance with the NEC and local electrical codes. When bonding the screen room to the building grounding system, use appropriately sized bonding conductors to connect the screen room's metal frame to the building's grounding electrode system. The bonding conductors should be sized in accordance with the NEC and should be installed in a manner that minimizes impedance. Ensure that all connections are made securely and that they are protected from corrosion. When coordinating with the electrical inspector, provide them with detailed plans and specifications for the installation, including the size and location of the isolation transformer, the grounding electrode system, and the bonding conductors. Be prepared to answer any questions they may have and to make any necessary changes to the installation to comply with the applicable codes and standards. Remember that electrical work can be dangerous, and it should only be performed by qualified and experienced personnel. Always follow safe work practices and use appropriate personal protective equipment, or PPE, when working with electricity. If unsure about any aspect of the installation, consult with a qualified electrical engineer or electrician. When dealing with sensitive electronic equipment, such as that used in pulse power experiments, it's crucial to minimize electromagnetic interference, or EMI. EMI can disrupt the operation of the equipment and can lead to inaccurate or unreliable results. Here are some additional measures that can be taken to minimize EMI in a screen room. Firstly, use shielded cables for all signal and power connections. Shielded cables have a conductive layer that surrounds the conductors, which helps to block EMI. Secondly, install filters on all incoming power lines. Power line filters can help to block EMI that is conducted into the screen room through the power lines. Thirdly, ground all metal enclosures and equipment to the building's grounding electrode system. This helps to create a low impedance path for EMI to ground. And fourthly, use proper grounding techniques to minimize ground loops. Ground loops can create circulating currents that can generate EMI. In addition to these measures, it may also be necessary to use specialized EMI shielding materials to further reduce EMI levels in the screen room. These materials can be applied to the walls, floor, and ceiling of the screen room to create a Faraday cage, which is an enclosure that blocks electromagnetic radiation. When selecting EMI shielding materials, consider the frequency range of the EMI that needs to be blocked and the level of shielding required. Also, ensure that the materials are compatible with the environment in the screen room and that they meet all applicable safety standards. When installing EMI shielding materials, follow the manufacturer's instructions carefully. Ensure that all seams and joints are properly sealed to prevent EMI from leaking into the screen room. Also, be sure to ground the shielding materials to the building's grounding electrode system. Remember that minimizing EMI is an ongoing process. It may be necessary to make adjustments to the shielding and grounding system over time to maintain optimal performance. Regular monitoring of EMI levels in the screen room can help to identify and address any potential problems. When installing an isolated ground system, it's important to understand the difference between grounding and bonding. Grounding is the process of connecting a conductive object to the earth to provide a path for fault current to flow back to the source. Bonding is the process of connecting two or more conductive objects together to create an electrically conductive path between them. In an isolated ground system, the isolated ground rod provides a path for fault current to flow back to the isolation transformer. The bonding conductors connect the screen room's metal frame and equipment to the building's grounding electrode system. The purpose of bonding is to equalize the potential between different conductive objects. This helps to prevent electric shock hazards and to reduce EMI. When installing bonding conductors, it's important to use appropriately sized conductors and to make secure connections. The bonding conductors should be sized in accordance with the NEC and should be installed in a manner that minimizes impedance. All connections should be made securely and should be protected from corrosion. In addition to bonding the screen room's metal frame and equipment, it may also be necessary to bond other conductive objects in the screen room, such as metal conduit and cable trays. The goal is to create a continuous, low impedance path for fault current to flow back to the source. When installing an isolated ground system, it's also important to understand the concept of impedance. Impedance is the opposition to the flow of alternating current, or AC. It is similar to resistance in a direct current, or DC, circuit, but it also takes into account the effects of capacitance and inductance. In an isolated ground system, it's important to minimize the impedance of the grounding and bonding conductors. High impedance can limit the flow of fault current, which can increase the risk of electric shock hazards and EMI. There are several factors that can affect the impedance of grounding and bonding conductors, including the length of the conductors, the size of the conductors, and the type of material used for the conductors. To minimize impedance, it's important to use short, large conductors made of a highly conductive material, such as copper. Also, ensure that all connections are made securely and that they're protected from corrosion. In addition to minimizing the impedance of the grounding and bonding conductors, it's also important to minimize the impedance of the grounding electrode system. This can be achieved by using multiple ground rods and by ensuring that the ground rods are properly installed. The ground rod should be driven deep into the earth and should be spaced far apart to minimize the impedance between them. When installing an isolated ground system, it's also important to consider the effects of transient voltages. Transient voltages are short-duration, high-voltage surges that can occur on power lines. These surges can be caused by lightning strikes, switching operations, or other events. Transient voltages can damage sensitive electronic equipment and can also create electric shock hazards. To protect equipment from transient voltages, it's important to install surge protection devices, or SPDs, on all incoming power lines. SPD are designed to divert transient voltages to ground, protecting equipment from damage. There are several different types of SPD available, including surge arresters, transient voltage surge suppressors, or TVSSs, and metal oxide varistors, or MOVs. The type of SPD that is appropriate for a particular application depends on the voltage level, the surge current capacity, and the response time. When installing SPD, it's important to follow the manufacturer's instructions carefully. Ensure that the SPD are properly grounded and that they are located as close as possible to the equipment they are protecting. In addition to installing SPD, it's also important to use shielded cables for all signal and power connections. Shielded cables can help to block transient voltages from entering the equipment. When installing an isolated ground system, it's also important to consider the effects of electrostatic discharge, or ESD. ESD is the sudden transfer of static electricity between two objects. ESD can damage sensitive electronic equipment and can also create electric shock hazards. To prevent ESD, it's important to take several precautions. Firstly, use anti-static mats and wrist straps when working with electronic equipment. Anti-static mats and wrist straps help to dissipate static electricity, preventing it from building up on your body. Secondly, use anti-static sprays and wipes to clean electronic equipment. Anti-static sprays and wipes help to neutralize static electricity on the surface of the equipment. Thirdly, control the humidity in the screen room. High humidity can increase the risk of ESD. And fourthly, use proper grounding techniques to minimize static electricity buildup. When installing an isolated ground system, it's also important to consider the effects of harmonics. Harmonics are voltage and current distortions that can occur on power lines. These distortions can be caused by nonlinear loads, such as electronic equipment, variable frequency drives, or VFDs, and uninterruptible power supplies, or UPSs. Harmonics can cause a variety of problems, including overheating of equipment, increased energy consumption, and interference with other electronic devices. To mitigate the effects of harmonics, it's important to use harmonic filters. Harmonic filters are designed to block harmonics from entering the power system. There are several different types of harmonic filters available, including passive filters, active filters, and hybrid filters. The type of harmonic filter that is appropriate for a particular application depends on the frequency range of the harmonics and the level of attenuation required. When installing harmonic filters, it's important to follow the manufacturer's instructions carefully. Ensure that the harmonic filters are properly grounded and that they are located as close as possible to the nonlinear loads. In addition to using harmonic filters, it's also important to use proper grounding techniques to minimize the effects of harmonics. Proper grounding can help to reduce the impedance of the grounding system, which can help to prevent harmonics from circulating in the system. When installing an isolated ground system, it's also important to consider the effects of electromagnetic fields, or EMFs. EMF are invisible fields of energy that surround electrical devices and power lines. Some people believe that exposure to EMF can cause health problems, although there is no scientific consensus on this issue. To minimize exposure to EMF, it's important to take several precautions. Firstly, maintain a safe distance from electrical devices and power lines. The strength of EMF decreases with distance. Secondly, use shielded cables for all signal and power connections. Shielded cables can help to block EMF. Thirdly, ground all metal enclosures and equipment to the building's grounding electrode system. This helps to create a low impedance path for EMF to ground. And fourthly, use EMF shielding materials to further reduce EMF levels. When installing an isolated ground system, it's also important to consider the effects of radio frequency interference, or RFI. RFI is unwanted radio frequency signals that can interfere with the operation of electronic equipment. RFI can be caused by a variety of sources, including radio transmitters, television transmitters, and cell phones. To minimize RFI, it's important to take several precautions. Firstly, use shielded cables for all signal and power connections. Shielded cables can help to block RFI. Secondly, install filters on all incoming power lines. Power line filters can help to block RFI that is conducted into the equipment through the power lines. Thirdly, ground all metal enclosures and equipment to the building's grounding electrode system. This helps to create a low impedance path for RFI to ground. And fourthly, use RFI shielding materials to further reduce RFI levels. When installing an isolated ground system, it's also important to document the installation thoroughly. This documentation should include detailed drawings of the grounding system, including the location of all ground rods, bonding conductors, and surge protection devices. The documentation should also include a list of all materials used in the installation, including the size and type of conductors, the type of ground rods, and the model numbers of the surge protection devices. Finally, the documentation should include a record of all tests performed on the grounding system, including the ground resistance measurements and the bonding impedance measurements. This documentation will be helpful for troubleshooting problems with the grounding system in the future. It will also be helpful for ensuring that the grounding system meets all applicable codes and standards. When installing an isolated ground system, it is important to periodically inspect and maintain the system. This inspection should include a visual inspection of all grounding conductors, bonding conductors, and ground rods. The inspection should also include a measurement of the ground resistance and the bonding impedance. If any problems are found during the inspection, they should be corrected immediately. For example, if a grounding conductor is found to be corroded, it should be replaced. If the ground resistance is found to be too high, additional ground rods should be installed. Proper installation and maintenance of an isolated ground system is essential for ensuring the safety and reliability of electronic equipment.